So let's look at this example. You're given some information. You're given the relevant formulae. And I want to see if we can work this out for both types of flywheel. A solid flywheel with a radius of 0.4. This radius is not the radius of gyration, it's literally the radius of the flywheel, so don't confuse the two. And here we've got another rim type flywheel with a mean radius of 0.6. You might well be given a situation where you're given the inner radius and the outer radius, so then you have to find the mean by adding them together and divide by 2. But in this particular case, you're given that the mean radius is 0.6. So let's have a go at this problem. Let's look at it for the solid flywheel and then for the rim type flywheel, and we'll set it out on this page. This formula is going to be useful. I'm being asked to find the torque for both types of flywheel. So what is the torque? It's the moment of inertia times the angular acceleration. And moment of inertia is given by mk squared. So if I know the mass, which I do, and I know the radius, I can find the radius. So I can find the moment of inertia. I feel fairly confident about that. And how can I find alpha? Use this formula here. So I need to know the angular velocity, final initial, and the time. I'm not given the angular velocity, I'm given the frequency in revolutions per minute. So that means I'm going to have to find those angular velocities. But that's the sort of thought process. So it's a bit involved. I write down what I know. So I can do that for the solid flywheel. Write down what we know. So we know the mass. We know the radius, we know the mass. We know the frequency initially and finally. And we know the time. So we can put in those values, and then we can think about calculating what we need. So if for the solid flywheel, we know what we've got, the mass, the frequency, and the time. If I know the radius, I can quickly work out the radius of gyration for a solid flywheel. It's just the radius over root 2. So I've got that information. I've got to convert the angular velocity, omega 1, is 2 pi times the frequency. I've sort of done that in one hit because the frequency needs to be per second. It's in revolutions per minute, so I've got to divide by 60. Divide by 60. So that gives me omega 1. I've just left it in terms of pi. Useful to do that if you can. Omega 2, again, 2 pi times the frequency, so that turns out to be about 73.3 radians per second. So we've got omega 1 and omega 2, so that means we can find alpha. The angular acceleration is just omega 2 minus omega 1 over 12, 0.87 radians per second squared. I've rounded that. You know, the more you round, the more inaccurate your answer is going to be, so hold on to some accuracy. Now I need to know what I is, the moment of inertia. So multiply the mass by the radius of gyration squared gives me this. And finally, the torque is the moment of inertia times the angular acceleration. So 7 Newton meters to one significant figure. We measure torque in Newton meters.
Can you go to the thing?
Yeah. Let's look at the second one now. I've got to repeat this now for a rim type flywheel, this one here. But let's approach it slightly differently. I know the formula for the torque, it's I alpha. So torque equals I alpha. What I can do, another way to do this is to leave it as a formula. I know for a rim type flywheel that I equals the radius, the mean radius, okay, times the mass, mk squared. Sorry, I know that the torque is going to equal the mass times k squared for a rim type flywheel times alpha, and alpha is omega 2 minus omega 1 over the time. So I can think of it almost like a formula. And algebra skills are going to have to come in here. But let me show you how this can make life a bit easier for you once you're used to it, and also give you a more accurate answer at the end. I don't know omega, but I do know it's 2 pi times the frequency. So I can leave this as mk squared. Well, k is just the mean radius. So that's the mean radius squared. So that's that. That's the moment of inertia. Times 2 pi times f2 minus f1 over time. I can put the whole lot over the time. So I can actually write the formula like that. This is the moment of inertia. 2 pi times f2 is omega 2, and 2 pi times f1 is omega 1. So actually I can take the 2 pi outside a bracket and just leave f2 minus f1 inside. If you see that, that's good, and you can maybe use this method. And then if I'm dividing by time, well, I could divide the whole thing by the time. So what I'm going to do now is put in the numbers and try and do this in one hit on the calculator. So the torque is actually the mass, which is 100, times the mean radius, which is, for this rim type, 0.6 squared, times 2 pi, brackets, f2. What's f2? It's 700 over 60, so I'd use the fraction button, minus 600 over 60, all over 12. And I can do that in one hit on the calculator, and that will give me the torque. And then I can round it to an appropriate accuracy. So just practice putting that in one hit on the calculator and see if you get the answer. We get 31.42, and we can sort of say that's more accurate because we've not been rounding. We've held on to all the accuracy. So I round that to say 4 significant figures, but I might well, taking into account the significance of the original numbers I'm putting in, round that. Now, I'm not saying do it that way. I'm just saying this is another way of doing it. If you want to, probably the way that's more, or at least errors involved with it, would be this first method, doing each one as you go along. So it might be a good idea to use this idea, work out what omega 1 and omega 2 is, and alpha and I, and then plug them into the final formula and see if you get the same answer and compare the accuracies as a little extension activity.